Hello, welcome to this week's physics. Alright, so this week we're going to be talking about electric potential. So, I'm just going to start with the first problem. Calculate the electric potential 0.115 centimeters from an electron. Okay, so this is the first electric potential problem we have here. I'm going to talk a little bit about electric potential. I'm going to treat this first problem as if it's the hardest one we're going to do out of all of them. That way we'll get the most solid understanding from this first problem, and we'll apply that then to the rest. Alright, so for starters, let's look at big picture here, big picture life. So you're going to see phrases like electric potential. And then you're going to see phrases like electric field. And we're going to see phrases like work. And we're going to see phrases like force. Alright, so electric potential relates to work. This is for any type of potential. Gravitational potential, I don't know, there's probably some other forces out there you can put the word potential after and it'd mean the same idea. The idea is electric potential relates to work. Electric field relates to force. So, and then the relation between electric potential and electric field is potential, which we're going to use V for volts, equals negative integral, E dot dr. And then for work to force, we have work equals integral F dot dr. I think this is a dot product right here. Alright, so same idea here. Force is a vector, work is a scalar, electric field is a vector, potential is a scalar. So, I hate the term electric potential. Whenever you see the phrase electric potential or electric potential difference, think of it as electric potential energy difference. You're like, what? You just took a simple concept and added more words to it. Well, I kind of did. So, and I didn't just say potential twice because it's, you know, not the whole dodgeball thing where potential is twice as important as the other words. It's not. So, electric here means that you're doing electrostatic charges, charged particles. Potential energy here means like potential energy. Like when you're talking about gravity, mgh. It's energy due to position. So, if you think of this in terms of gravity, then it's potential energy. This is joules. And the difference is because you need a reference point for all of them. Even though when they say, what is the potential? What they really mean is, what is the potential between whatever point they're talking about and infinity? Potential is always the difference between the two. And this potential here means what is the potential energy. So for example, if I relate this to gravity, and I say, I have a ball that's 10 meters off the ground. How much energy does this ball have? Here's the ground. Here's the ball. This ball is going to fall. And how much energy it has? Well, your first thought is mgh. Energy equals mgh. Really, that's just a simplification of force equals big G mass 1, mass 2 over r squared. And then you do work equals F dot dr. You work it all in there, and it simplifies basically to this, more or less. You know, when you're talking about plus the surface of the earth. So here you'd say, all right, we have 10 meters off the ground. So we know what height is, we know what gravity is, but I never told you what the mass was. So how can you know how much energy something has if we don't tell you the mass? Well, you could be like, all right, I don't know what the potential energy is, i.e. the energy due to the position of the ball that you're talking about, but I can't tell you the amount of energy depending on the, the kilograms of it. So I can give you the joules per kilogram that you're talking about. That way, if you're giving me a 10 kilogram ball, we raise it 10 meters, I can do the calculations, bam, tell you how much energy you have. So what we're talking about here in electric potential is measured in volts, which I think is tragic. Not that Volt was a particularly, I don't know enough historical history about him to tell him he's good guy, bad guy. I don't really care. All I know is that volts is a measure of joules per coulomb, which I always call it joules per coulomb because it makes a lot more sense. It's like, wow, joules, energy, coulomb, charge. So how much energy it has? Well, it matters how many coulombs you're talking about here. So when I say potential here, I mean here's the joules and here's the potential for how much energy can be there based on the number of charges you have. And the difference, because even if you're talking about just 1 point, you're really talking about that 1 point and infinity. Alright. So that's why don't we use this in, you were kind of told this concept in Physics 1, but they never really stressed it. They never really talked about the gravitational potential energy. Why that is, I don't really know. Why it's such a big deal in electrostatics, or with charged particles, but not with gravitational, I don't know. That I don't know either. So maybe it's just because when you start talking about circuits, potential is more useful. Maybe. I'm not entirely sure. Alright, so back to the first problem. Calculate the electric potential 0.115 centimeters from an electron. Okay? So we have our electron right here. And we have a distance of 0.115 meters. Is that right? Whoa, 0.115 centimeters. So this would be times 10 to the negative second meters. There we go. Okay? So we have basically two formulas that we associate with voltage. You probably have already seen the equation KQ over R. Specifically R, not R squared. You've probably also seen, and Parks already showed it to you, E dot dr. Well, this can also be rewritten as KQ over R squared integral dr negative, which, for terms of integraling, like integrating is actually the real term, it's better to look at it as r to the negative 2 dr, which is negative KQ r to the negative 1 divided by negative 1. There's probably supposed to be a plus c in there. I don't care. Negative, so then you get positive, because you have double negative, KQ over R. So the idea here is, if you have a vague idea of what both of them are, then, and you have one of them memorized, then you can use that to kind of figure out what the other one is. So you can either memorize this formula right here, or memorize this formula right here, and then know what E is. So either way, we'll be able to get you the formula. You need to know the formula. And this is here is specifically for a point charge. Alright. And I guess everything in life is made up of small points, so that's kind of the formula for everything in life. So let's see here. If we do this, then we have 0.115 times 10 to the negative second. That is, no, I don't want to do that yet. Let's cut straight to the chase. 8.99 times 10 to the ninth. That's K. We have an electron, so I will Wikipedia real quick. Wikipedia, Mr. Electron. Probably should pull up Wolfram too. There we go. And we get an electric charge. 1.602 times 10 to the negative 19th. 1.602 times 10 to the negative 19th over 0.115 times 10 to the negative second. There we go. Maybe I should simplify this a little bit. So 10 to the negative second is the same as 10 to the second on the top. 9 plus 2 is 11. 11 minus 19 is negative 8. Okay. So we'll do 8.99 times 1.602 times 10 to the 8th negative 8th divided by 0.115. We'll probably get a really small number. Now let's see, they want them in volts, they want it in volts. Alright. So we have, oh, that's not as small as I thought it was going to be. 1.25 times 10 to the negative 6. (1.25 times 10 to the negative 6 volts, or as I like to say, joules per coulomb. Okay? So one other thing I should mention here is what this actually means. So what this is saying is, if we have our electron right here, and we take another particle and we move it from infinity, which I'm going to say is over here, not drawing a scale. Oh, that's infinity right there. Actually, I could say that's infinity too, but it doesn't matter. Same idea. It's saying how much energy, just like dropping the ball 10 meters, how much energy does it take to bring a particle from way over here all the way over to 0.115 centimeters from the electron? Well, it's going to matter how much of a charged particle you bring. So that's why our answer is going to be in joules per coulomb. Coulomb being the charge that we're bringing in. So on that note then, a little bit on notation, I would write this as V115 centimeters infinity. Usually they don't put a little comma in there, but I like to sometimes. So what I mean by this is KQ over 0.115 times 10 to the negative second minus KQ over infinity. So this is still the electron here. Now since this is infinity, any number divided by infinity, assuming it's not infinity itself, will then be 0. So this part we just ignore, which is why they don't even write it in. So I like to write it in because that way it's just a little bit more clear. Okay? So next we're going to go to what is the magnitude of the electric potential difference. Again, I say electric potential difference is the exact same as electric potential, except this time they're giving us the second point. So they're saying that they're giving us 750.750 centimeters instead of infinity. So what is the electric potential difference between 2 points that are that far and that far from the electron? Okay. So I'm going to draw it like this. Electron, this will be 0.115 centimeters. I'll say times 10 to the negative meters. And I'm going to draw it down here. There we go. And this is going to be 0.75 centimeters. So it's saying, what is the magnitude of the electric potential difference between 2 points? Okay, they're asking for the magnitude, which specifically does not matter direction. So we bring a particle in from infinity to point, let's call this guy A, let's call this point B, or bring in a point in from here. These will both give us a number, a joules per coulomb. So we could say then that this might be, I'm just throwing this number out here, 1004 joules per coulomb. So this would mean that this is a negative charge. By moving it closer, we're like compressing a spring between the two. And we could say this one might be 1,002 joules per coulomb. So what this would be saying then is the potential difference between A and B would be this area right here, which you'd logically look at and be like, oh, well that's 2 joules per coulomb. Because you take this guy minus that guy. So if I was going to write this out in a more formal manner, I would say voltage AB equals voltage A infinity minus voltage B infinity equals KQ over A minus KQ over infinity minus bracket KQ over B minus KQ over infinity. Right. And then you would look at this and you'd be like, oh, distribute the negative sign. The negative infinity in the bottom is going to go to 0, so it doesn't matter. And you get KQ over A minus KQ over B, which will then just equal KQ 1 over A minus 1 over B. So this is probably the formula that they give you, where they say voltage AB equals voltage A minus voltage B. The first number minus the second number. Okay, that's true. I like my way better because it's more obvious what you're actually trying to do in life. But it's still true. So to do this real quick, we have 8.99 times 10 to the 9th times 1.602 times 10 to the negative 19th all over. Nope, not going to do all over yet. Over 0.115 minus, what is it, 0.75? 0.750. And then they're centimeters, so I'm going to put like 10 to the second on top. Wolfram this real quickly, so I get something a little bit simpler. Actually, I'm going to fix the exponents. 9, ooh. Right. 9 plus 19 is 10. Negative 10 plus 2 is 8. Yeah, close enough. Excuse me. (1.44) times 10 to the negative 7th. 1.44 times 10 to the negative 7th times 1 over 0.115 minus 1 over 0.750. Alright. So, looking at this straight from a logical point of view to start with, it's going to take, assuming they're both negative charges, it's just easier to visualize if they repel each other instead of attracting each other to start with. So we're going to grab a particle from here and drag it all the way to A, which is closer to the charged particle. That will be more difficult than dragging a particle from infinity and dragging it all the way to B, which is further away. So it makes sense that the 1 divided by 0.115 would be bigger than 0.750. So we'll get a positive number. Now, one quick adjustment. Formula up here for number 1 was negative. Q is negative 1.602. So that negative carries around up over here. Alright. So, right. If these were both positively charged, okay, so if these were positively charged and we were bringing it, then they would attract each other. So the work, it would actually be easier to bring them together than to do nothing at all. Therefore, we'd represent that by having the work as negatives. Because positive, negative, So it would have a negative potential. So then the negative potential between A and B would be negative. And it matters then if you're moving it from B to A, which would give you, assuming these guys are positive, if you move it from B to A, you have a negative potential because that'd be easy. And if you had a positive charge, it's being attracted to the negative charge, you move it from A to B, then it would be positive because it would take work to pull your positive charge away from the negatively charged electron. So I am going to calculate this guy out real quick. 1 divided by 0.115 minus 1 divided by 0.750. Don't really need that extra 0, but I'm going to put it anyway. And you get 1.06 times 10 to the negative 6. 6, and this would be joules per coulomb, or more commonly known as volts. Alright, so 1.06 times 10 to the negative 6 volts, or joules per coulomb as I like to say. Alright, then part C, how would the answers change if the electron were replaced by a proton? Alright, so this goes back to what we discussed earlier. We just got to see when the charge matters and when it doesn't. So voltage is kq over r. Therefore, even though voltage is a scalar, it can be positive or negative. Therefore, this q, if it's a proton as opposed to an electron, would then flip the sign. So the sign of A would change. Now for the sign of B, what is the magnitude of the electric potential? Magnitudes are always positive. Magnitude, think of it like as a distance. You don't have negative distances, mostly. So magnitudes are always positive. So A, the sign of A is not, or sign of B is not going to change no matter what. The sign of A will change. So sign of answer A would change. That's true. Sign of answer B would change. No, it's not true. Sign of both would change. No, both answers remain the same. No. So it's only the first one. The sign of answer A would change. Alright? And that's a quick overview of what you need to know about potential. Or, as I like to say, in overly verbose terms, electric potential, potential energy, difference. Electric potential, potential energy, difference. Alright. See you on the next problems.